So in this smart contract security topic, we're gonna see two classic vulnerability or two classic attack. The first one is called a re-entrancy attack, which is one of the most classic attack in the block in the smart contract. And the second attack is called an overflow-based attack. We're gonna see two overflow attacks. First one is integer overflow. The second one is buffer overflow. All right, so first let's look at re-entrancy attack. What is re-entrancy attack? The re-entrancy attack is actually involves two smart contracts. We have a victim smart contract. We have an attacker smart contract. So the victim contract actually maintains the cryptocurrency asset like Ether. And the attacker contract aims to steal the cryptocurrency asset from the victim smart contract. Okay. And we're going to see how can the attacker steal the asset from the victim smart contract. And at a high level, this attack works by we ask the victim smart contract A to call the attacker smart contract B for execution. However, the attacker smart contract call back the victim smart contract again, right? Which just the victim contract call the attack contract, which call back the victim contract again. So that's just re-enter the victim contract. So that's why we call it re-entrancy attack. You allow the victim, you allow the attacker to enter the victim contract multiple times. Right, this re-entrancy attack. So the very first re-entrancy attack happened in 2016 in a smart contract called DAO. The DAO is a victim smart contract exploited by the re-entrancy attacker. The attacker exploited this vulnerability and stealed $150 million from the contract. All right. So eventually, it leads to this Ethereum Classic and Ethereum hard fork. Okay. So in 2016, right, Ethereum experienced a hard fork. Right. So the reason is that because of this attack, a group of people argues that we should roll back the blockchain stake and to recover the loss. And such a group of people, they agree on to roll back and continue the blockchain. So that's called which is today's Ethereum. So today's Ethereum actually roll back this DAO attack. However, there's another group of people disagrees the rollback. They said we should not violate this kind of blockchain's irreversibility nature, right? We do not allow, right, rollback. We should not allow rollback in the blockchain for any cases, right? So they believe that, so they disagree this kind of rollback. So that group of people decides to extend the blockchain in the classic way. So that's called Ethereum Classic blockchain. So actually, if you look at the Ethereum ecosystem, actually there are two separate blockchains. One is the Ethereum mainnet, which already rolled back this kind of attack. But there's another chain called Ethereum Classic, and that chain does not roll back this attack. Okay, so because of that kind of disagreement between these two parties, so there's a fork. Okay, there's a fork.
Was the rollback that transaction and all the transactions afterward, or just
exactly? Yes. rollback or no, only rollback is attacker transaction. For any other transaction, they're gonna stay. They just like remove the attacker's transaction, so the funds are still in the DAO contract. Okay. So again, I mean, because the amount is too high, right? So there's a reason for such a rollback. But for individual victims, like if you lost probably $1,000 US, they're gonna ignore it. They will not roll back the blockchain for you, right? Because the loss is not smooth. But at that time, right, 150 million, right, it's a huge amount of asset. Right? So that's the reason that a lot of people, they kind of agreeing, okay, we should roll back. Okay, so the DAO attack actually is the most, classic attack back, 10 days ago, 10 years ago. So again, this DAO contract is a victim contract. It contains a vulnerability which allows the re-entrancy attack happen. So to understand this re-entrancy attack, there are some preliminary background information we need to understand first. So the first one is fallback functions. Okay, so I trust all of you have know, right, the fallback functions. So the fallback function essentially is a backup function in the case that the function you call is not implemented. They're gonna execute the fallback function, right? So if you are calling any undefined functions, they're gonna execute the fallback function for you. So and another one is that in the smart contract, you can send Ether to another address, including a UA address as well as a contract address, right? So there are two different ways that we can send Ether inside the smart contract. The first one is we use the receiver address .send, and the amount of Ether is the argument of the send function. That's the first approach, right? The second approach for sending Ether is we use receiver address .call .value. Okay, so you can also and then the data, you can put data after the value, which is the argument, including the function hash and argument. So that is two approaches for you for the smart contract to transfer Ether to another address to another smart contract. So the gas inside the value actually is the amount of gas for calling for executing the execution, and the data actually includes the function hash and the argument list, right? So when you are just want to transfer the Ether, normally we just include an empty data, right? Because we don't want to execute any functions. We just want to transfer the Ether. So the data normally will be empty, right? We're just transferring Ether. So if we just send a transaction, not a transaction, a call. You will send a call to callee, not caller, callee with the rest of gas. So here is one example. So we can inside the smart contract, we can use this address .call and give this amount of gas, and the parameter is a hash of this function signature, right? This function signature, The function name is foo bar. It takes 2 integer as the argument, and then you can just pass the 2 integer as the argument. Eventually, they will be encoded as the core data and then sent to the target address for execution. So if this address is a smart contract, then in a smart contract, there should be a foo bar function. Okay. Okay, right? So now let's look at the re-entrancy attack. So let's look at this. This is the victim contract. Inside the victim contract, there is a mapping. It's a balance. It maintains the user's balance, like how many ether are deposited from the user, right? There's a balance mapping. And then inside, of course, there is a deposit function which accepts the ether from the user, right? So there is another function called withdraw balance. In the withdraw balance, whoever calls this withdraw balance function, first, we're gonna read the callers, which is message sender, right? Message sender is a caller. We're gonna read the caller's balance, which is the amount to withdraw. That is we're gonna read the user's balance, the caller's balance, and then we're gonna use this message.sender.call.value, which is amount to withdraw. We're gonna transfer this amount of ether to the message sender. That's second step. Right? Step 1, we read the balance of the caller. Then step 2, from the smart contract, we transfer to the caller all his balance. Right? Step 2. Step 3, we're going to update the user's balance to 0. No problem, right? Are there any problems inside this function? We check the balance. We read the balance. We transfer all the balance to the caller. Then we update the balance to 0. But essentially, if you look at the step, we read the balance, we transfer, we update the balance. Right, this is sequence, right? The sequence of these 3 steps. Read the balance, transfer the balance, transfer the amount, then update the balance to 0. Any problems? There gotta be a problem, but it's an interesting problem. Normally, like this one, from the logic, right? No problem, right? There's no logic flaw, right? So let's say I'm the attacker. I first deposited 1 ether to this contract, and then I call withdraw. Then I will receive the 1 ether back, and then I'm gonna call it again, and this time I cannot withdraw anything, right? Because my balance is updated to 0, right? No issue, no problem. However, the problem, actually there is a problem. The problem occurred in step 2. When the contract executing this statement, the attacker can use a smart contract. And then the attacker's smart contract first deposit 1 ether to this contract, and then call withdraw. So the withdraw function gets executed. The withdraw is going to execute step 1, and then step 2. If you look at step 2 this time, they're gonna call back the attacker's contract and make a transfer, right? And normally, then the withdraw function will continue the execution in step 3, right? However, in step 2, when this victim contract executes the second statement, it actually invokes the attacker smart contract, right? And say the attacker, so which function in the attacker smart contract will be executed? The fallback function, yes, because there's no argument, there's no function hash, right? So what the attacker can do is that in my fallback function, normally, right, we can implement anything inside the fallback function, right? The attacker inside the fallback function implements a statement which calls the withdraw function again in the victim contract. So now you can say, normally, right, we execute read in the first step, transfer in the second step, then we're gonna enter the attacker's contract. The attacker's contract, the fallback function, it invokes the withdraw function, so which go back to the step 1. And then read the balance. The balance is still okay, right? Because step 3 has not been executed so far. So the attacker's smart contract still has the balance, right? So, okay, pass, and then do the second step, transfer. Transfer either to the attacker contract and then call the fallback function. The fallback function then calls the withdraw function again. So you can say it keeps entering this withdraw function again and again to drain the whole balance. This is why it is called a re-entrancy attack. Any questions? Okay, I have a demo for you. So let's look at the attack. So I have this re-entrancy demo contract. So the victim contract is a store, is a bank essentially. It's a bank contract, right? There is a balance mapping, and there is a deposit function which accepts the payment from the user, and then update the user's balance, right? By adding the balance with the message value, right? No problem. And then in the withdraw function, it first read the user's balance and require that the user's balance is bigger than 0. And then it execute this message.call, and the value is the balance. It just transfer the user's balance to the message sender. And then check the send. If it's false, that means there's an error, then the function will terminate, right? So if the send is successful, then it updates the user's balance to 0, right? Message sender to 0. No problem, right? The get balance function is just a reading is actually reading the contract's balance, right? The contract's balance. Okay. Now let's deposit this Ether store contract and see if it works correctly. So I'm gonna maybe let's just refresh the web browser so that the balance are just gets reset. Re-entrancy, compile. Okay, I'm gonna deposit this Ether store contract from the first account. The first account actually has 100 Ether. I'm gonna deposit it. I'm gonna deploy this Ether store contract. Okay, Ether store gets deployed. Okay, the withdraw and the deposit function get balance 0, right? There's nothing inside this contract. I'm gonna deposit from the first account 1 Ether. Okay, so the transaction is successful. Get a balance. Okay, 1 Ether, right? 1 Ether are inside this contract. Now I'm gonna use the second account to deposit another Ether. Okay, another 1 Ether. Deposit. Get a balance. Okay, 2 Ether here, right? You can see obviously balance is 2 Ether. Now let's use the third account to withdraw. Can the third account withdraw? No, right? Yes. The transaction failed, right? So the balance is still 1 Ether. Nobody else, only the first one, the second one can withdraw, right? So now let's check if the first one can withdraw. Withdraw, okay, okay. Balance 1 Ether, and what is my balance? 99, almost 100, okay, good. Let's use the second account, withdraw. Okay, balance 0, balance 99, 99, okay. So both two accounts can deposit, withdraw what they have deposited, and then nobody else can deposit. I can withdraw. No problem, right? Seems to be okay, right? When the developer tests this smart contract, okay, no issue. Now let's see what the attacker can do. There is a attacker contract. Okay. Actually, there is some warnings, but never mind. What is the warning? Okay, doesn't matter. Okay, so the attacker contract actually first it initialized the Ether store contract with this Ether store object, and then inside and then there is an attack function, the attacker's contract. In the attacker function, the amount actually it requires the amount is 1 Ether. So it requires that the attacker to send 1 Ether, which is okay. We can do that, right? One amount is message value is bigger than 1 Ether. Okay, we can do that, of course. Then we're gonna call the Ether store dot deposit. We're gonna deposit this 1 Ether to the Ether store, right? And now after the deposit, I'm gonna call this contract is going to call Ether store dot withdraw. To withdraw that 1 Ether. Just like in the same function, in the attack function, you first deposit 1 Ether and immediately withdraw it. No problem. But if you look at the fallback function, in the fallback function, actually, it checks if the Ether store's balance is bigger than 1 Ether. If it's bigger than 1 Ether, it executes the Ether store withdrawal again. Go back to the re-entrancy workflow, right? So normally, right, when we call the attack function, we're gonna first deposit 1 Ether, and then we're gonna withdraw that 1 Ether. So the withdraw function will be executed inside the victim contract, and it read the balance. So the balance, which is the message sender is the attacker contract, right? Attacker contract just deposit 1 Ether. So the balance is 1 Ether, right? And then it's going to execute message.sender.call and transfer 1 Ether to the message sender, which is the attacker contract. This is the call, right? This is a call. It calls the message sender, which is the attacker contract. So attacker contract, the pullback function will be executed and receives one ether. So there are two things happening. One ether will be received by the attack contract. Then the fallback function will be executed. Right? So the fallback function, when the fallback function gets executed, it actually executes the withdraw again, which enters the withdraw function again, and which checks the balance of the caller. The balance was not updated, right? So it's still one ether. You call this attack contract function, attack contract again, transfer ether. So another ether gets transferred to the attacker. See, okay, let's see. So, okay, so this is the ether store contract that we have deployed before, right? We just tested it. It's okay, right? No problem. Now let's use the first account to deposit ether again. Okay, deposit ether, and use the second account to deposit one ether. So the balance is 2 ether in the victim contract, right? No problem. Now let's say I'm gonna switch it to the attacker, which is third account. The attacker is going to deploy the attacker contract. So when you deploy the attacker contract, we need to pass the ether stores contract address in the constructor function, right? We're gonna pass the victim contract's address to the construct function and then deploy the attack contract. So now the attacker contract is deployed. So the attacker's contract balance is 0, right? 0. Now, still the third account, right? I'm gonna transfer one ether to the attacker contract and call the attack function. So eventually that one ether in the attacker's function will be deposited to the ether store contract and then then withdrawn, right? Withdraw. Let's do the attack. Becomes 3 ether. 3 ether. And look at the victim contract ether store, 0 ether. Previously it was 2 ether, right? 2 ether. Both 2 ether from the first account, second account are stolen by the attacker through this re-entrancy vulnerability. Good. And then let's say the first one, the third one, okay? So the ether now is inside the attacker's contract, right? So the attacker can just call the withdraw function and withdraw all 3 ether. So you can say eventually after withdrawal, it receives 102 ether. This attack is interesting, right? Interesting. If you're the developer of the victim contract, you probably believe, okay, it's safe, no problem. We read the balance, and then we transfer, and then we update the balance. That's why in the DAO attack, right, 150 million US dollar was stolen, because the attacker drains all the ethers from the DAO contract. So now how to fix the problem? Just demonstrate the attack and talk about how the attack works. So now how can we fix this problem in smart contract?
Don't let your code be reused by someone else.
How can you prevent that?
What's that?
How do you prevent your code from being re-entered, right? If you make the withdraw function private, then nobody can withdraw, including the depositor, right? Let's say the first account, the second account cannot execute the withdraw function.
But you don't have to have two contracts. Like only one deployable.
Yeah, just the first one. Yeah. Yeah, we can just have one contract, right? The either store, we deposit that contract, and then everybody can deposit and withdraw. No problem. There are no the second contract is deposited by an attacker. It cannot prevent an attacker from deploying contract. Always fix the problem. In the withdraw function, in the victim contract, they first read the balance, then transfer the ether to the caller, which could execute a fallback function and then re-enter, right? So there is no way to prevent this from happening, right? What else can we do?
Update the balance to 0 before you initiate the transfer.
Very good. Let's see. How about we switch the order and do the third step first before second step, right? So let's so first one is read, right? Read the balance, and then we update the balance. And then we do the transfer in the third step. We know the third step is going to call the fallback function in the attack contract, which then enters the read enters the withdraw function. Then can the attacker steal ether? Because in the first round, right? In the first round, the balance is updated to 0. Then in the third step, 0 will be transferred. Right? So this is a one strategy, one countermeasure. Is one countermeasure, one possible countermeasure. So you see, actually the order matters, right? The 3 steps. So because if you look at the problem, what is the problem? If we look at the problem, let's create a new slice. If we look at the problem, actually in the withdrawal function, There are 3 steps. First one, read the balance. Second one, transfer. Third one, update the balance. If we write a function, if we write the whistle function in this way, there is a race condition problem if you look at this order, right? There's a race condition problem because we're going to execute it 1, 2, 3 in order. However, step 2 is going to trigger another execution of 1, 2, 3. Right? So if we just change the order to step 1, we read the balance. Then we update the balance before the transfer. We are safe. So the key step is step 3, right? Step 3 is the most important step because it moves the font, right? It moves the ether. So if you write a program in this way, and then this could be a race condition. There is a race condition problem. So yeah, for students in my, if you have taken my computer security class, right, we have actually talked about race condition. Okay. Computer security class. Okay, why not? Why not just do a quick demo to see if by changing the order and see if the attack can still success. Uh-huh.
So now if it fails on step 2 though, you got the balance wrong.
Step 2.
Go back. Sorry, I should have said soon. Go back to the last. So it fails after step 2.
On the left or on the right?
On the
Left
right.
hand or right hand? Right hand side, okay. Step 2. We up the balance, no problem. You just change the mapping. You change the balance mapping, right? Set the balance to 0. What is the problem?
I'm just thinking, because it's not all happening at the same time, right? I'm just thinking if something happened and it stopped at step 2, and there's no transfer balance, internal counting is off at that point.
You mean we update the user's balance without transferring the funds to the user?
Right.
How could that happen? You mean we ask you the first step, no problem. We ask you the second step, no problem. We ask you the third step, there's a problem. Execution stop. Then we just go rework, right? If the transfer failed, we just do a rework. So step 1, step 2 will be rolled back.
Then can't that be exploited?
Say again?
Can't that be exploited?
Can't
Can
that
the attacker
be-
exploit that? Because you're saying that if the transfer fails, then we revert.
Right.
But could an attacker exploit?
How do you exploit it?
I don't know, I'm asking. I don't know. I'm not sure how.
how can the attacker exploit this revert? The attacker can the attacker see anything?
If the transfer fails, the attacker's not gonna get it.
Right.
So you can just get nothing as a result.
Nothing. Eventually nothing. So what is the problem? The attacker cannot get any benefit. Right? So if you look at the program, if you look at the order 1, 2, 3 on the right hand side, if the attacker wants to receive some money from the account, first one he has to have some balance to pass first step, right? And then there's no way for the attacker to skip the second step and then go to third step. But on the left hand side, before the third step, in the second step, you allow the attacker to enter the function again, which means you keep letting the attacker to pass the first step without updating the balance in the third step. Okay, that's the issue. Okay, just let's do a quick demo. We don't have to require there is a balance. Of course, if we do require there is a balance, then when the attacker contract re-enters the withdraw function, it's going to fail, right? It's going to fail because this is the third step. That's this second step, right? This second step. Let's put it before the transfer, right? Let's put it before transfer. Okay, so now just refresh the web page. Re-entrancy. Okay, first step, second step, third step, transfer. Now let's deposit from the first account. Deposit with the is a store contract. Is a store is deployed, and then transfer 1 Ether from the first account. Okay, balance is 1 Ether. Second account, transfer 1 Ether, deposit 1 Ether, 2 Ether, withdraw 1 Ether, received 1 Ether. First one, withdraw 0 Ether in the contract, 1 Ether received. Okay, oh, good, right? Deposit, withdraw, both are okay. Now let's do the attack. So from the first one, deposit 1 Ether. From the second one, deposit 1 Ether. Oh no. Okay. Modify this one. Oops. 1 Ether. Oh my God. 1 Ether. Deposit 2 Ether. Okay, 2 Ether. So both took address, get almost 99. Okay, 99. Now I'm gonna switch to the third account to do the attack. Deploy the attack contract by copying the victim contract's address, deploy it. So deployed attack contract is here. I'm gonna call the attack function with 1 ether from the third account. Okay, third account. Attack, right? Failed. Transaction failed. 0 ether. Still 2 ether. If we look at the problem, right? We just fix the problem by changing the order, right? Changing the order. Another countermeasure is that, okay, assume let's use we still want we still want the previous order, which is we read the balance first, and then do the transfer, and then do the update. But this time, we're gonna use send function to send the balance. This can also fix the problem. Okay, expect. Okay, send. Message dot send dot send. Payable. Okay, payable. Driven number of components on left hand side, then right hand side. Okay, so we should not. There is no return for the sender function. So any problems here? Okay, transfer. Transfer. Let's use transfer. Transfer just equivalent to send, right? Transfer. I'm going to do transfer. See if we can defend against this re-entrancy attack. Let's say. Re-entrancy demo. Okay, first step, read the balance, transfer, and update the balance. We're gonna deploy the victim contract and deposit 1 ether. From the second account, deposit 1 ether. And then from the second account, withdraw. Okay. Okay. From the first one, withdraw. 0 ether. No problem, right? Then I'm gonna deposit 1 ether from the first account. Deposit 1 ether from the second account. And then let's do the attack. Deploy from the third account. We're gonna deploy the attack contract. Deploy the attack contract is deployed. And then from the third account, we're gonna call the attack function with 1 ether. Failed. Transaction failed. So the victim still has 2 ether. So what is the magic here, right? We just, instead of using the message sender.call, we use transfer. What is the magic here? We still allow the order of read, transfer, update. But in the transfer step, we do not use message sender.call, we use message sender.transfer. And I'm pretty sure that if we use message sender.send, can also defend against this attack.
That's making sure that it calls that withdrawal function instead of the other contracts.
The transfer, right? The transfer eventually we also call the fallback function. Right? Transfer, if you look at the message sender, not transfer. Message sender is the attack contract, right? They execute the transfer function in the attack contract. There's no transfer function in the attack contract, so the fallback function will be executed. But there's a problem. Any match? The ranges is still could happen, but it is not happening. In the previous one, we just use in the vulnerable one, we just use message sender, right? I forgot the main, essentially just message sender dot call value, which is I think it's this one. Is the balance. Previous one is using the this one, right? This message sender dot call, and now we change it to message sender dot transfer. So the guess for these two statement is different. The guess is limited to 23,000 if we are using transfer. That means in the victim's withdrawal function, when it executes the transfer statement, it only gives 2,300 to the target contract, to the target address to execute, which is only enough for the transfer of Ether, and not enough for executing the fallback, the logic in the fallback function, which thus prevents the attack contract from entering the virtual function. Right? In this one, if we're using message.sender.call, guess is unlimited. That's why it allows the attacker contract enters the visual function again and again. Oh, good, right? So everybody knows guess, right? Guess. Guess is the budget, right, for the execution. So, okay, so defense countermeasures. First one, we should not use call.value. We should use send or transfer, right? Transfer. Because both send and transfer has a limit for the guess. It only allows 20,300 guess for the execution, which is enough to send Ether, but not enough to run a function. Okay, function.
Shouldn't be maximal.
Oh, okay, yeah. So I need to update. maximum 23, okay, 2300. So the second difference is we should make internal change before external interaction. This means we should update the balance before calling the message sender, right? Just like we do the update before the transfer, right? So that's the second difference. We finish our internal work first, right? We check the condition and then update the state of our contract, and then we interact with the external contract. The second difference. So, okay, I don't have to talk about the example of second difference, right? Just do the update, right? Do the update before the transfer. However, the second difference actually has some limitations because it requires the developer, right, to follow this kind of pattern, right? Follow this paradigm. So the check effect interaction, right? So the second difference essentially is such a pattern: checks, and then update, and then interaction. And actually, it is hard, right? It's hard to write the code, right? You cannot make sure, you cannot guarantee all the developers follow this pattern, right? So if you can follow the pattern, that's good, but people can make mistakes, right? Developers can make mistakes. So just you can use the first one, use the send and the transfer to transfer either. Or the third difference is that you can use mutex. You can use a locking, right? Locking mechanism. Right. So mutex is the locking mechanism in external contract calls, right? We first acquire the lock. We start the locking, and then we do the external interaction, and then we after the external interaction we just release the lock, right? So the locking essentially is just a very classic defense for risk conditions. If you remember that in my computer security class. So, for example, the risk condition happens when you have multiple processes that access the same data, right? Same resource. Let's say one process read the data, one process write the data, another process write the data, right? So how do you prevent them from corrupting the data, right? You just sequential that access, right? When the first process are reading the data or writing to the data, I'm gonna lock this data, so nobody else can write to the data. Right? That's just a locking mechanism. Right? So same idea can be applied to defend against this re-entrancy attack. We can use lock, right? So in this case, the balanced mapping is the shared data, right? Shared data, right? So whenever we update the balance mapping, we're gonna use a lock. We're gonna set the lock to true, and after the update, we release the lock. We set the lock to false. Right? Like in the deposit, we do that, and in the withdraw function, we also do that. We also do this. We lock the balance, and then we do the balance update, and then we release the lock. Right? We set the lock to false, so that when you enter the withdraw function first time, the lock balance is true, and then when you re-enter this lock function, the withdraw function, the lock balance is true. which does not satisfy this condition, right? Right. In order to enter this withdraw function and to update the balance, the lock balance should be false, right? And then if you already entered, we set the lock to true. So if you enter it again, you will not satisfy this condition, right? Okay. So these are just a locking mechanism. You only allow them to enter once. All right, so that's all about the re-entrancy attack, right? So it is one of the most classic vulnerability in the smart contract in the Solidity. So the second type of attack is called an overflow attack. Okay, the first one, let's look at an integer overflow. We all know that in this Solidity, in the smart contract, the integer actually has a range, right? So the biggest one is unsigned integer 256, right? That is the largest integer that we can use inside the smart contract. And what if we have a number, we do a calculation in the smart contract, which is 2 to the power of 256 plus 1. Such a big number will be a negative number, right? So that's just an overflow, right? Integer overflow. The integer overflow could happen inside this smart contract as well. So let's say we have a vulnerable function called a transfer. It first checks if the sender has enough balance, right? It requires the balance, so it allows the two address to withdraw the value, and then it checks the balance of the sender and say if it has enough balance than what he is withdrawing, right? Withdrawing from the contract. So that's a check. And then it subtract, it add the balance, it subtract the balance of the sender and add the balance of the receiver. Okay. But these two just unsafe. It can cause integer overflow as well as underflow, right? Because you're gonna overflow this number 256. So the difference is to check the overflow conditions. Okay. Let's do a quick demo maybe to see this integer overflow attack. I have a integer overflow demo. Actually, we have a time lock contract. In the last lecture, we talked about time lock, right? Time lock. So it has a deposit function. It accepts a deposit from users and update the user's balance. And then there's a lock time. The lock time for the depositor is the current block plus 1 week. That means when you made a deposit to this time lock contract, you can only withdraw after 1 week. Right? This is time lock, right? And you can also increase your time lock with this increased time lock function, right? So if you call this increased time lock time, we're gonna increase the lock time for you by the value you send, right? That's good. You can also increase your lock time, right? Let's say you don't think one week is enough, I'm gonna lock 1 month, then you can call the increased lock time, right? And there is a withdraw function. which first checks if you have enough balance, and then requires that when you call this withdraw function, the block time step should be bigger than the log time, right? That means the log time already passed, right? You can withdraw. And then it updates the balance and a transfer. Let's say if okay, maybe do we have, okay, we have 2 more minutes. Let's compile this one and deploy this time log contract from the first account. Maybe use the first account, okay, the fourth account. Deploy it, okay. Deposit, withdraw, right? We deposit, withdraw. Let's deposit 1 ether, okay, 1 ether, withdraw, okay, withdraw failed. Withdraw failed. Why? Right, you have to wait 1 week, right? After 1 week, you can withdraw. Let's say, okay, I don't want to wait 1 week. I want to withdraw right now. What I can do is I'm going to deploy the attack contract to exploit the integer overflow vulnerability. Okay, so what I need to do is, okay, I'm going to copy the time log contract to the deploy function and then deploy the attack contract. And then I'm gonna call the attack. Okay, fail. Okay. Let's do the let's use the fifth account to deposit 1 ether. So you can look at here in the time log contract. There is still 1 ether, right, locked by the first account. I'm using the fifth account to deposit another ether. So if you look at the attack contract attack function, it called this time log contract the deposit 1 ether, right? And then it called this time log increase log time, and this is a magic number which is going to overflow the log time, and then it calls the time log withdraw. Let's say, okay, let's say, okay, ether 1 ether is withdrawn. And because the increased time log time, the number we put, the argument we put inside this function is just a very big number, which is going to overflow the log time for the depositor, right? So namely, if we can find a good argument for this increased log time, that is going to overflow the log time to a small number, we can withdraw.